Okay, so let me make sure this is recording. Yeah. So this video is going to be about evaluating limits. In the last videos, we kind of wrote limits down based on the graph or tried to sketch something that followed certain limit rules. This one, we're going to actually try to figure out what the limit values are. First one is just an extension of the last handout. Find important features of this graph and write down limit statements for them. So if we look at this region right here, that's probably the most important region. That's going to be the limit as x goes to 0. If I said from the left side, then the function itself gets really close to 1, right? Because as I come at it from this side, the values get close to 1. But it's also true from the right side, so I could write this same statement but put a plus here. But that's really no different than the minus one, and if both the minus and the plus go to the same value, I can just say the one value without a minus or a plus. So as x gets close to 0, y gets close to 1. Let's see here. Let's look at, in fact, you know what? This function is so important that I want to write it with those in there. Sine x over x. That gets close to 1 as x gets close to 0. This function actually comes up a decent chunk, and it's very useful for an algebraic trick. The other thing that I would probably do is I want to show you this idea. As x goes to 0, sine x over x gets close to 1. We can see that graphically. This is really no different from me saying this. 6x goes to 0. Sine of 6x over 6x turns into 1. Right? That actually kind of says the same exact thing, except I've just replaced all the x's with 6x's. And this is also a useful trick right there. Okay, so then let's look at, as x gets really big, this graph actually tapers out more and more and more. And as it goes very negative, same thing happens. So we can write that as limit as x goes to infinity of f of x. So that's way out here on the right side. That turns into 0. The y values go to 0. So this actually says we've got a horizontal asymptote at y equals 0 on the right side. And then we could actually say the same exact thing for on the left side. That also turns into 0. So we got a horizontal asymptote at y equals 0 on the left, too. Another thing that you can do with this is you can actually say, if we look at it with the function written in place instead, let's do that. Sine x over x. Well, if you think about what sine does, sine always has to be between -1 and 1. And so sine x over x, well, if I just keep plugging in infinity, or just bigger and bigger numbers, this top always just bounces back and forth between -1 and 1, whereas the bottom just keeps getting bigger and bigger and bigger. So that's a way that you can kind of figure out, oh, well, it's some number between -1 and 1 over like a billion. Well, that's got to be close to 0. And then you could do the same exact thing as x goes to negative infinity. The sine x part is still bouncing back and forth between -1 and 1, but the x value just keeps getting more and more negative. So that turns into 0 too. So you can think of it this way as well. So here are the other two important limits that we can pull out of this graph. Okay, let's do an analytical one. So no graph, right? So in this one, we're looking at a function that happens to be continuous around x equals 2, right? And how do I know that? Well, it's a quadratic function, and so it's a parabola, and all polynomials are continuous everywhere. So let's say the parabola looks like this, and I don't really care where x equals 2 is on this graph, but let's just say it's here, right? This is 2 comma f of 2. And what I'm asking here is what's the limit as I get close to 2? And there's no sign associated with the limit, so that means both x goes to 2 from the left and at the same time x goes to 2 from the right. So as I'm coming at it from the left, whoops, that's the right, from the left and the right, I'm getting close to whatever this value is right there. But that value we can figure out pretty easily. It's just f of 2. So since the function's continuous, so we'll call this function f. Since f is continuous around x equals 2, we can say that the limit as x gets really close to 2 of that function is just whatever f of 2 is. And f of 2 is 2 squared plus 3 times 2 minus 5, which is, what, 4 plus 6, so 10 minus 5, it's 5. All right, so continuous functions are easy. If I give you a continuous function, or a function that's just continuous where you want to actually take the value, then just plug it in and you're done, right? Okay, so let's look at this next one. Limit as x goes to 2 of this thing here. So this one, let's call this f. So f of x, I'm going to do a little side work over here. F of x equals x squared minus 5x plus 6 all over x squared minus 4, which I can factor, so that becomes x minus 3, x minus 2 over x plus 2, x minus 2. Now you might remember that this means, since the x minus 2's, are really just a form of 1 here, if I were to cancel them, I'd get this picture instead. But that's not quite the same function, because that means the one thing that differs between the graph of g of x equals x minus 3 over x plus 2 and f of x, which has these x minus 2's here, is that g of x has x equals 2 in its domain, whereas this f of x does not have x equals 2 in its domain. So that means that there's actually a hole in the graph of f, so a removable discontinuity at x equals 2. But it does have, this thing tells us it's going to have some vertical asymptote at x equals negative 2. So hopefully you remember those ideas from chapter 2. This one then is actually nice and continuous. This one still has the vertical asymptote at x equals negative 2, but it's continuous at x equals 2. This one has some hole at 2 when x is 2. This one, it's the same picture except that the hole is filled in at x equals 2. So this one's g, this one's f. Okay, so then what does that mean for our limit? So here's what we do. This is kind of the way that a lot of people will write this stuff. It's the limit as x goes to 2 of the original, right? So I'm just going to start with the original problem. And then I'm going to say, well, that's the same thing as this. All I'm going to do is put the function in factored form. X minus 2. And so this function right here, around 2, has that hole in it, right? I don't know actually what the graph looks like. I just know that around 2 it's got the hole. So what we want to do is, and all I care about is what's the value right around 2. So if I could plug that hole somehow, then I could just plug in 2. So in order to plug in the hole, all we have to do is cancel the x minus 2's. We got x minus 3 over x plus 2. This is the extended function right here, right? The extended function fills in the hole. And so now, in order to get that value, I can plug in 2 into this function right here. So that's 2 minus 3 over 2 plus 2, which is going to be negative 1 over 4. Okay. So the strategy here, the main idea or main strategy and this is going to be true for a lot of these limits. If the original function that you're taking the limit of has a removable discontinuity where you want to take the limit, so that's like this example. It had a hole at x equals 2, so we couldn't just plug in 2 because it wasn't smooth there, right? It wasn't continuous there. Well, then the goal is, try to come up with an extended function that is continuous at that place. Right? Because if you can come up with a function that's continuous there, then all you need to do is plug in the point, right? So let's see how long this video is getting. Okay, so let me do one more example with you. We'll do this bottom one here, number 4, keeping this strategy in mind. Okay, so the function here, we're doing limit as h goes to 0 of 3 plus h squared minus 9 over h. And if I simplify the top, then this is going to be limit as h goes to 0 of 9 plus 6h plus h squared minus 9 all over h. And then I can do a little simplification. The 9's cancel, and I could say limit as h goes to 0, and I'll just factor out an h here from the numerator. So this is the same exact function in factored form. And if you notice, the h's, they, in a sense, could cancel. So this function, that's the whole function right here, should look like the line 6 plus h, except that 0 is not in the domain. So, it looks like this, except 0 is, 0 is not in the domain. So there's just a hole at 0. But I can come up with an extended function where it's the same exact picture, but the hole is filled in at 0. And then if I care about what happens just to the left and to the right of 0, what the y value is, I could just plug in 0 into that new function. So that new function is when I cancel those h's. Right. So that fills in the hole at 0. So since I care just about what happens close to it, I'm just going to plug in 0 to get that value itself. So it's going to be 6 plus 0 equals 6. Okay, so this one right here, removable discontinuity at x equals 0. So the trick that we do is we find the extended function that has the same graph, but with the removable discontinuity filled in. So now it's continuous. Well, at least it's continuous at x equals 0. So then, again, the point is that way you don't have to try to analyze it any other way except you filled in the hole, so just plug in the value and you can get what these arrows are pointing at. Okay, I'm going to stop there and then continue on another video.